One. Boop. Welcome back, everybody. Hey, just so you, just to say it again, in case you didn't watch the video yesterday, the quiz is going to be next Tuesday. We're doing section 6-4 today. Today is Thursday. Tomorrow, we're going to be doing an exponent review. Make sure you bring your computers tomorrow. I will be asking you to watch a video for part of the lesson. So make sure you bring your computers tomorrow, fully charged, ready to go. Okay. For tonight's homework, with the exception of Tabia, I don't think you are in the online or program yet. I have to ask somebody about that. So you don't have to. Tabia is the only one that is excused from tonight's homework. This is through the Big Ideas website. It's already assigned to you. Okay, so know that tonight's homework assignment is on the Big Ideas website. Everybody should know how to get there. The link on the side and everything. That's true. Yes, that's what that is. All right, so let's take a look here. We're going to see if it's linear, exponential, or neither. Can somebody tell me, and this is just like the basic gist of yesterday, what should you see, what pattern should you see if it's exponential? If a function is exponential, what pattern should you see?
If the y values are doubling?
It could be doubling, but could it also be like tripling?
Oh, yeah.
Yeah.
So multiplying by itself?
Exactly. Multiplying by some value. And that could also be multiplying by a fraction, or as you guys would probably say, division. Okay, so if it's multiplication or division, it's exponential. What would it be if it was linear?
It would be like plus
or minus, right? Okay, so let's take a look at this first one. Look at the y values. What's happening in the y values?
They are dividing by 2.
They're dividing by 2, right? So what can I say about that? Somebody raise your hand and tell me. What can I say about that then? That it is exponential. Good. I'm not asked to create exponential. I'm not asked to create the equation. I'm just asked to say, okay, is it linear or is it exponential? Because I see its division. Couldn't I have also written this as multiplied by 1/2? Isn't that the same thing? Right? So I could change it into multiplication if I needed to. And I would need to if I wanted to build that equation. Take a look at number 2. Is that linear or exponential or neither? Linear. What's the pattern in the y values, Kenny?
-1.
Good. -1. So I'm going down 1 each time. So that tells me that it's linear. Questions about that? Now, I do want to go over at least one of the graphing problems because, well, half of you didn't do them, and some of you did not do them correctly. But are there any questions 1 to 15 on? 17. Yeah, 1 to 15 on. Are there any questions on any of those? Yeah. Yeah. 15. Let's take a look there. So 15, let me get these out of the way. I'm just asked to plug in, so 1/3 times 6 to the 3rd power. So I just go in here and I say 1/3 times 6 to the 3rd power. You know what I'm going to do? Parentheses first. 6 to the 3rd. 72. Make sense? Question?
On the test, do we only have to write 72?
Yeah.
Okay.
In the key, I kind of spelled it out for you, but no, 72 is just fine.
Okay.
Any other questions 1 to 15 on? Okay, let's go over one of these 3 questions. Does anybody have any preference? Nathan?
17.
Let's go over 17. That's the one I went over last period too. And I'm thinking if you messed up 17, it might be because of the negative. Now, let me ask you, is the negative in parentheses? No. So we don't include that when we square it and take to the negative 2nd power. Now remember, when we make our x and y table, and I had a lot of people not make the tables. How do you know you need to make the tables? Because that's what we did in our guided notes yesterday. Guys, if there's a problem in your homework that you don't understand how to do, look at your guided notes. I hope you have seen by now that I go through the guided notes, I go through the homework, and I make sure there's an example of pretty much every type of problem within the guided notes, okay? So if you don't know how to do a particular problem, look back at the guided notes, and that might help you out. Like you may be thinking, how do I graph this? Well, how did we do it in our notes yesterday? We made a table of values, okay? We made a table of values. negative 2, negative 1, 0, 1, and 2. And all I do is just plug in. So I'm going to go to my calculator, and I'm going to say negative 4 times, oh, sorry, not negative 4 times, negative 4 to the negative second power. Now notice, did I do any parentheses? You should not have done any parentheses because there is no parentheses in the original equation. So this is negative 0.06. Negative 1, same thing, negative 1. Negative 0.25. Negative 4 to the 0 power is negative 1. Negative 4 to the first power is negative 4. And then negative 4 to the second power, negative 16. Now, I didn't really need to calculate all those out once I see a pattern. What's my pattern? Multiply by what? 4. And look at the base of the exponent. 4. Okay? So you should be able to start recognizing those patterns. I'm continually multiplying by 4 each time. Yeah, question, Nathan.
Yeah, so when we do those x values, it doesn't matter if there's a parenthesis with a number inside of it for the equation.
Say that one more time.
So, like, you know how number 17 doesn't have the parenthesis with a number in it?
Yeah.
So, like, it's still the same thing?
Still the same thing.
Oh, okay.
Yeah. Like for 19, you would just do 3 times 0.05 to the negative 2.
Oh.
3 times 0.05 to the negative 1, and so on and so on and so on.
Okay.
Yeah. Just do it exactly as you see it on the page in your calculator. All right, so here's negative 1, here's negative 2, here's positive 1, here's positive 2. Now we got to go all the way down to negative 16. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Perfect. All right, so we have negative 2, negative 0.06. So it's like right next to the line. We've got negative 2, comma, negative 0.25. So pretty much still in the same spot. And then we have 0, comma, negative 1. 1, comma, negative 4. 1, 2, 3, 4. And then 2, comma, negative 16. All the way down here. Now, remember, you should know by now, because we talked about it yesterday, what the look of the graph should be for any exponential. It should be a smooth curve. Should it be a line? No, which is why I was confused when I was walking around and seeing a lot of lines. It should not be a line. It should be a nice, smooth curve. And then remember, there was that thing about that asymptote that we talked about yesterday. Should it cross the x-axis? No, it should not cross the x-axis. Questions about that? Yes, I got a notification.
It just opened because it looks like I'm looking at it because I was doing now.
Any other questions on the homework? Hopefully that cleared things up for the graph. Okay, that's what you should have done on 17, 19, and 21. I should have seen a table with 5 values and then a full graph. Questions about that? Okay, let's get to today's notes then. Now, I think you're going to find that today's notes ties right in with yesterday's notes. Okay? You know, I said earlier section 6.1 and 6.2 tied very closely together. And now section 6.3 and 6.4 tie very close together. Remember that the quiz is going to be next Tuesday, and it's going to be all through section 6.1 all the way through the end of section 6.4. So after we get done today, by the end of today, you will know everything that's going to be on the quiz next Tuesday. Okay, so again, section 6.3, Luca, turn around. Section 6.3, we were talking about generic exponential functions. And what does an exponential function look like? How do we tell if something is exponential? And then we created the graphs of the exponential functions. Now, the basic generic exponential function, a times b to the x, that was when we had just a number times another number raised to the x. And we said that number outside was the starting value times the constant multiple, constant ratio to the x power. Now, I could not think of anything more real life than exponential growth and decay right now. Not only because of the pandemic, but we're going to talk a lot about money today. Okay, we're going to talk a lot about money and exponential growth and exponential decay of money. Okay, if that doesn't make your ears perk up, I don't know what will. So let's talk about exponential growth. That's our first thing here, exponential growth, because things could go up or things could go down. So we're going to have exponential growth and then exponential decay. Let's talk about exponential growth first. Exponential growth occurs when a quantity increases by the same rate in each time period, t, or r. In this case, we're going to talk about it as our x value. When this happens, the value of the quantity at any given time can be calculated as a function of the rate of the original amount. Like, for example, say I invest like $50,000, because I'm rich. Say I invest $50,000 into an account that's going to give me 7%. What's that?
10% a year.
So $50,000 into an account of 7%, right? What that means is I'm going to take that $50,000 and it's going to give me 7% of that $50,000 at the end of the year. It's going to give me that 7% back over on itself, okay? Now, at the end of the first year, do I just have that $50,000 in my account anymore? No, I've grown. I've grown 7%, whatever 7% of $50,000 is. Now, end of year 2. It's going to account for not only my original investment of $50,000, but my interest that I earned the year before, my 7% interest that I got the year before. So it's going to do what's something called compound on itself, because I've got not only the interest, not only my initial investment, but also the interest that I've earned over the course of the first year. So it's going to calculate 7% on the 50, whatever, probably like $55,000 or $56,000. Then it's going to do that again the third year, and then it's going to do that again the fourth year, and it's continually going to be calculating interest on not only my initial investment, but also the interest that I earned on the year before. So it's going to snowball. It's going to get big quickly, which is exactly like an exponential function. 53,500. Thank you. So now what's going to happen, though, is that interest is going to get calculated on even more interest. Now, how mathematically what happens? What is the equation of that? Go ahead, star it, circle it, do whatever you need to do. Whoa, where are we going here? This equation right here is very important. That's my exponential growth equation. Y is equal to a times 1 plus r to the x power. A times 1 plus r to the x power. Now, remember yesterday, what was my number outside the parentheses? It was our starting value, our y-intercept, correct? Same thing here, but now we just talk about it as like our initial investment, the original value, the starting money, whatever it may be. If maybe population is increasing. Now, what's key to exponential growth is the fact that we have a percent rate. We're growing by a percent rate. Like, for example, growing at 7% per year. Here's the deal. And everybody please underline this. In decimal form. That's extremely important that a lot of people forget. You have to be putting our percentages in decimal form. So like 7% should get shifted to be 0.07. And then we raise it to the x power. Now that x power is going to be our time periods. So if I say, okay, I want to calculate this over the course of 15 years, 15 would be my x value. That 1 is standard. The 1 is always there, which makes sense because if it's going to be a rate, it's got to be above, and it's going to grow, it's got to be above 1. So I'm going to add my rate to 1. So it's going to make it grow. Decay is a different story. We'll talk about that in a second. So let's take a look at this one here. A value of a painting is $9,000. The original value of a painting is $9,000. And the value is going to increase 7% per year. 7% each year. Write an exponential growth function to model this situation. So let's pause and just do that piece. Now, remember that my growth function is a times 1 plus r to the x power. A times 1 plus r to the x power. Ladies and gentlemen, what is my a value? What's my a? 9,000, my original value, my initial investment. What's R? 7%. And now, remember, I'll write it like this, but we should always remember 0.07. You have to make it a decimal. Please don't say 0.7. That's 70% growth. And trust me, I'll put my whole nest egg in 7.7 because that's 70%. All right, now let's plug everything into my equation. Y is equal to 9,000. I'm going to show this for the first couple problems, but then I'll stop. 1 plus 0.07 to the x power. Because what's 1 plus 0.07 going to become? 1.07, right? So 9,000 times 1.07 raised to the x power. That's my your exponential function. Now it says, okay, see what's going to happen over the course of 15 years. Over the course of 15 years. 9,000 times 1.07 to the 15th power. Let's calculate that out. 9,000 times 1.07 raised to the 15th power. Almost $25,000. 24,831.28. 24,831.28. So you may be thinking to yourself, oh, 7%, that's not that much. Oh, but if things are growing exponentially, growing at a continual rate, it's going to get big quick. Yeah. Oh, yeah, you can have it. Okay.
Give me Opa, 15 years.
That's a long time.
That's like not fast.
Yeah.
I'd still be under 50.
I'm not even 50.
Nice. All right, let's take a look at the next one. I don't know why this is still art, but sculpture. We have a sculpture, and it's increasing at a value. Its value is increasing at a rate of 8% per year. And its value is in 2018 was $1,200. Write an exponential growth function to model the situation, then find the sculpture's value in 2024. So same thing here. It's going to grow. Now, how do I know that this is going to be exponential growth? Because I see increasing by a percent. That's how I know that I want to use this formula. Exponential growth, increase by a rate. Tommy. A times 1 plus r to the x. So what's my A value again? $1,200. What's my R? Don't give me a percent anymore. Just go straight to the decimal. 0.08. Please don't say 0.8. 0.08. Okay, let's create our equation. Again, I'm going to write the 1 plus for one of the steps. 1,200 times 1 plus 0.08 raised to the x. And then I'm going to reduce it here. 1,200 times 1.08 to the x power. That's my equation. That would tell me any year. If I wanted to calculate this all the way out to 2050, I could. If this same pattern will continue. Okay, now let's figure out what it's going to be. What do I plug in for x in this case? I've got 1,200 times 1.08 to the 2024?
6.
To the 6, because 6 years have elapsed. Let's see what that's going to be. 1,200 times 1.08 raised to the 6th power. It's going to get me 1904.25. Okay. So while it was only 8%, it was only over the course of 6 years. So it's not a really long amount of time. You want investments to grow big, you got to leave it in there for a long time. Especially if it's just growing at a specific rate, specific percentage rate. Okay. Now, remember, the thing that I see people mess up on the most is not moving a decimal, right? Make sure you move the decimal. Question, Nathan?
Nope, I'm good.
Okay, so this is exponential growth. But do things always increase? No. Things tend to decrease as well. We could also have exponential decay. Now, we're not always talking about money here. We could have like population decay. We could have like, Anybody study half-life in science classes? Like half-life is exponential decay, things like that. Exponential decay is just basically things going down at a certain rate. Things going down at a certain rate. So what's the only difference? Look at the equation on your page. What is the only difference between exponential growth and exponential decay? It's subtraction instead of addition. It is subtraction instead of addition. That is the only piece that's different from exponential growth to exponential decay. And what's going to happen is that rate is going to get pushed underneath 1. Like if it decreases 10%, it's going to be 1 minus 0.1 or 0.9. And since that value is below 1, it's going to make the values of my function decrease and decrease and decrease. And that's exactly what I was talking about down below here. Notice that the importance of that 1 there being added or subtracted, that's going to make it grow or decay. So let's take a look at my next example. This is on the top of the back. The population of a town is decreasing at a rate of 3% per year. In 2020, there were 1,700 people there. Write an exponential decay function to model the situation. And then we're going to figure out what it's going to be like in 2032 if that pattern continues. All right, so y is equal to a times 1 minus r to the x power, right? How do I know it's minus? Because the problem is referencing something going down by a percentage. All right, my a value, my initial amount, this time it's not a money, it's a amount of people, so 1,700. My rate, 0.03, please don't say 0.3, 0.03. Now, you know I said I was going to skip that step with the 1 plus in the growth? I'm not going to skip that step ever when I'm doing decay. 1,700 times 1 minus 0.03 to the x power. I'm never going to skip that step. Never. 1 minus 0.03 is 0.97. So y is equal to 1,700 times 0.97 raised to the x power. That's my exponential decay function. Now it then says, figure out what's going to happen in 2032. How much time has elapsed from 2020 to 2032? 12 years. So we have 1,700 times 0.97 to the 12th. Let's see what the population is going to be. 1,700 times 0.97 to the 12th power. So if this pattern continues, we can expect the population to decrease to 1179.53. Now, I know we're talking about 0.53 of a person, but what I'm doing here is I'm predicting a future value. So it's not actually talking about a concrete person. Okay? When you're actually predicting, it's okay to use decimals, and that's all right. Because we're talking about a future person, not a concrete actual person. Let's do one more of these. Fish population is decreasing at a rate of 2.5% per year. All right, so my A value in this case is 48,000. That's my original fish population. My R is 0.025. Be careful. 2.5% is 0.025. So when I go into my equation, it's going to be y is equal to 48,000 times 1 minus 0.025 to the x power. Subtraction, because again, I see it's decreasing at a rate. So this is 1 minus 0.025, which in this case is 0.975. 48,000 times 0.975 raised to the x. So there's my equation. And then I'm going to take that equation and figure out what's going to happen over the course of 7 years. Over the course of 7 years. So 48,000, 0.975 to the 7th power. 48,000 times 0.975 raised to the 7th power. And that'll tell me after 7 years of 2.5% decrease in population, it's going to go down to 40,204.4. 40,204.4 fish. Okay. Just over the course of 7 years. That's a lot of fish. But it just decreased 8,000 over the course of 7 years. So that's like a pretty big decrease, right? Yeah, Nathan?
Since this is a word problem, do you have to put a label?
I mean, I guess. Fish.
Like it's not required in
Fish.
Okay.
Yeah.
I just didn't know if we had to, like back in 8th grade.
Picture label. Yeah, Brennan? Yeah. Okay, now, what we're going to do now is talk about it in terms of identifying exponential growth and decay based on a table. Not write down those last two problems. There you go. Okay, take a look at this first one. Take a look at this first one. Is this exponential growth, exponential decay, or neither? Now, if it's neither, you will not see that constant ratio pattern. What's happening in terms of a pattern of my example A?
Decay.
It's decay. What's it going down by? I'm asking Gia. What's it going down by each time?
30%.
Oh, I like what you're saying there. I'm dividing by 3. Dividing by 3. Yeah. Dividing by 3. And since it's decreasing, I could say that, yes, this is exponential decay. Exponential decay. Example B. What's happening there, Henry?
Growth.
How do you know it's exponential growth?
Because it's doubling each time.
Good. Times 2, times 2, times 2. All right. Now, what about example C? Is that growth or decay, and why? Nathan?
Exponential growth because the R value is more than 1.
Good. More than 1. Can somebody tell me, because this actually gets asked in the homework, what's the rate? What's the percentage rate at this when this is increasing? 7%. Good. 7%. How do we see that? Well, it's 1.07. Take the 1 away, we got 0.07. That's a 7% growth. All right, what about D? Decay. And how do you know it's decay? Because that's less than 1. Now, can anybody tell me the percentage decay? What's the percentage decay? Noah? 2%. Good, 2%, because I'm subtracting 0.02 from 1, right? So it's a 2% decay. Good. Okay, this is my last example here, and I actually don't love compound interest. I'm very surprised that this is still in the standards. We kind of took it out from teaching this a couple years back, like 5 or 6 years back. And then about 3 years ago, this showed up on the end of course test. And we're like, oh, I guess we should teach this again. It's called compound interest. The same rules apply. But think about it this way. In the beginning of class, I said, okay, every year, I'm going to calculate my interest, right? What if I didn't just do it every year? What if the bank said, okay, we'll give you interest every half of a year. Every 6 months, we'll calculate your interest. Well, what if a bank said, okay, what if we'll do it every quarter? 4 times per year, we're going to calculate your interest. Or what if a bank said, okay, every month we're going to calculate your interest? How does that change my equation? Well, it's still the exact same type of equation where I've got my initial amount on the outside. I've still got the 1. I still see the rate in there, but the only new variable is n. N is the amount of times I get compounded per year. So say I was going to do it every month. If I say compound monthly, How many months are in a year? So 12 is my n. If I said compound quarterly, there are 4 quarters. So I would say it's going to compound 4 times within a year. So basically what you do is you divide the rate by n, and then you also put that n in the exponent as well. Okay. A lot of bank accounts use compound interest rather than just standard yearly interest. So let me show you one example here. So again, the formula is y is equal to p. Again, p stands for principal in this case. Principal is just my initial amount. 1 plus r over n to the nt. Okay, let me ask you, what is my initial amount in this case? 1,200. My next variable up is my rate. What is my rate? What's my rate? No? 2%, so 0.02. What is my n in this case? Danielle? 4, thank you. 4, because I'm compounding quarterly. How many quarters in a year? 4. That's why it's compounding quarterly. It would be 12 if I was going to compound monthly. What about compound weekly?
55.
56.
7. There's 7 days.
Nobody's got it.
Weekly's 55. There's
52.
55 weeks in a year.
52, thank you. 52 weeks in a year. Yes. Trust me on that one.
Only 52?
I thought it was 55.
I don't know.
There's 4 weeks in a month, and there's 12 months.
That seems short.
52. All right, and then what's my t value? That's my 3. That's my time. And now all we have to do is just plug this in. So y is equal to 1,200. 1 plus my rate over n. Shh, stop talking while I'm up here. I'm really getting very sick of Tommy and Noah just talking to you up here.
That wasn't us.
Stop. Well, you do all the time, and you're not taking notes, obviously. And now all I have to do is just calculate this out. Let's run it in our calculator here. 0.02 divided by 4. I'm doing this here, that's 0.05, so that's my rate. 1 plus 0.005. 1.005. I'm going to put that in there. 1,200. 1.005 raised to the 4 times 3 is 12. 1,200. 1.005 raised to the 12th power. 1274.01. So honestly, only over the course of 3 years, I'm only going at 2% rate. It's going to give me just about $74 over the course of 3 years. Why so small? Because I'm not going at a long enough time. I'm not increasing at a long enough time. I need to wait. Can't make my investment back that quick. All right. Remember to bring your computers tomorrow. Oh.